I can't do this today.
All right, so let me get the screen on. So I think we are recording. It's good. All right. Come on, screen. All right, so we are on to know how to do that. Okay. So all right, we are on to chapter 5.
Oh, yeah, day 18.
Oh, day 18. Okay. 5. This is all about magnetic fields. All right, so we are gonna do most of chapter 5. I told you we're not doing chapter 6. And I have to look at the schedule. Maybe I said that, but I'm pretty sure. Let me just check. I might as well check. So this video, you will not actually see this because I'm not sharing that screen, but give me a second here. Let's go check. Yeah, no chapter 6. And then we'll be doing electrodynamics, some of it. Let me check that as well because
So we weren't doing magnetic fields in media.
Yeah.
Not just-
yeah. Um, This drives me crazy that I can't tell what is the Moodle screen. So scrolling down. So we are in week 5. Week 6, we have, yeah, we do go into chapter 7. And we have a test next Friday. And we'll be doing 7. The schedule's all messed up, so I will figure it out. But I'm assuming up to like 7-3, maybe 7-4. Okay. All right. But anyway, we're in chapter 5. Okay. So, we've been dealing with static charges that don't move, but if you allow them to move, we talked about how you are going to get some magnetic fields, right? If you allow your charges to move. And so this is where we're going to start is thinking about magnetic fields today. And then Thursday and Friday, we'll be doing kind of the next, well, 5.2. This is really 5.1. Okay. All right. So let's just consider a current going down a wire. Okay. And if we brought a test charge near the wire, it wouldn't feel any force, right? I mean, there's charges that are moving in a current, you know that. But a test charge would not feel any force, right, from those charges. However, if you brought a compass near it, you definitely would get that compass needle would move, right? So we know that there's something going on. And let's draw some pictures. I've got that in another sheet here. All right, so let's draw a picture. We have a wire. And we have some current going up the wire. And in general, the magnetic field, if you remember from 116, around that wire will be these kind of circular field lines. Now, obviously the field lines aren't circles, right? So if I was going to draw this with actual field lines, I would draw it more like, well, let me erase it and show you what I mean. So we draw circles just because it's a real pain to draw arrows in a circle. So we would draw it more like, little tiny arrows that are changing direction, right? But it's such a pain. Look how long it takes me to do that. And it looks crappy that we just draw circles with an arrow. Does this make sense? Okay, just FYI, right? They're not really going in a circle. The magnetic field is changing directions around the wire. Okay, does this make sense? So I will draw it with what we usually do is kind of these circles with an arrow showing the direction of change. And if you go away, farther away, it gets weaker. Okay, and if we were really drawing it with this is kind of the downside of drawing it with a circle is that how do you know it's weaker? You don't. Whereas if you were drawing it with little arrows, right, those arrows would be less dense. That make any sense? Okay. All right. So okay. So let's look at an example where we have two wires. So I'm going to have another wire here. Wire 1. And I'm going to draw the magnetic field even just a little bit different than that, which is another way to draw it. Because, by the way, I didn't really point this out, but those circles that I've drawn, those circles are meant to be in and out of the board, right? They're not like just sitting in a plane. They're in and out of the board. So a better way to draw the B field is to have it where we have an arrow coming up on this side and the tail of an arrow going down that side. I want to call that B1, right? Does that make sense? Because it's going into the board and coming out and going in and coming out, yeah? Okay, now what if we have a second wire? Okay, so we have a second wire with current I2, okay? Let's look at the force on wire 2 due to wire 1. All right. So over on this side, if I wanted to draw what is the B field that wire 2 experiences at its location, it's going to be in this direction, right? Yeah. And we know that the Lorentz force for magnetic fields is, so this is B1 again, right? This is B1. The Lorentz force, if you remember from 116, is F magnetic is Q V cross B, right? And so, but of course, V is well, let's back up a tiny bit. So we have a B field at wire 2 that's in moving charges, right? That are going at velocity V, which is basically the current, right? So you have some charges moving at velocity V. And so if we want to know at least the direction, right? We want to know exactly what is the direction. What is direction of the force, okay, due to wire 1, well, the B field, I guess, due to B1, how about that? And this will be on wire 2. Okay, we just want to know what the direction is. We use the right-hand rule, right? Because it's a cross product. So we put our fingers in this is what I do. You guys have your own thing, I'm sure. But I always put my fingers in the direction of the velocity, right? Which is the direction of the current. And then I cross down because B is going into the board. And so my thumb now is pointing to the left, right? That's your left, isn't it? Yeah. And that's the force, right? That's the direction. So here, if we want the direction of the force, we use our right-hand rule. So this wire is going to attract the other wire. And in fact, parallel currents attract, right? So we see that parallel currents what would happen if the if I2 was in the opposite direction? Yeah, so how would we do that? We would put our hand down, cross down into the field, and we'd be going the opposite direction that way. So the force would be pushing pushing that wire away from it. I don't know if you guys have ever done that experiment in 116. I don't remember if we do that in 116 where you just have two wires and you change the current and they, do like this or like this. They should do that. Or just if Sheldon does that in a demo, I don't know. It's cool to see because you just literally just switch the current and they will either attract or they'll come together or they'll go apart. Okay. Okay. So fine. So this Lorentz force is for just the magnetic forces, but of course, if we also had an electric field, you could add in the electric field. So if we have both, so this is kind of in my way. I'm gonna move it. I never can figure out if I can move this without like doing things to it, which I don't want to do. So if we have both laying around, the total force is going to be QE, right? We know that's the force, plus V cross B, right? Okay. Now let's note a very, very special property of magnetic fields, which I'm sure you've heard somewhere, hopefully in 116. Okay. So give me a second. Are we ready to go to the next layer? Okay. Okay. So wait, what happened? Okay. So magnetic fields do no work. Very important property of them. They cannot do work. All right, well, let's think about it. So why is this the case? All right, if you have Q and is moving an amount, it moves amount dl, little vector dl, or dr if you like, and that's given by its velocity dt, right? Okay, the work would be dw is of course f dot dl, right? But of course here would be the magnetic field would be doing the work. Let's see what happens. So this would be F mag dot dl. And we know that F mag is Q V cross B, okay? Dot V dt, right? Because that's what dl is. Okay, why can I immediately tell that this is 0? Why?
Because V cross B is perpendicular to.
It sure is. And so when you dot it with whatever that is, whatever V cross B is, you dot it with V, you get 0, right? Okay. It cannot do work. Now, magnetic fields can change the direction of things. We know that, right? You send a particle into a magnetic field and it'll start circling around, right? It can change a charged particle that's moving. It'll change its direction, but you can't slow it down or speed it up with a magnetic field. Okay. Okay. So that's really important to just know. It's not like we use that all the time. All right, but let's start writing our forces in terms of current instead of Q, right? QV. So let's define current. What's that noise? Okay, fine. Not a fire alarm of any kind. Okay, so recall that we define, oh, my bad. Define current. It's charge per unit length. Okay. Sorry, what did I say? Charge per unit length, charge per unit time. I'm thinking length for some reason, time, right? Charge per unit time. And remember that, you know, we always think of currents as being electrons flowing, but it's actually the opposite. Right? If you have a current flowing down, if you have I, the electrons aren't moving in that direction, right? The electrons are actually moving in the opposite direction. So we think of the holes as moving in that direction, right? So they're leaving and the positive and leaving positiveness, and that positiveness is traveling up because the electrons are traveling down. Anyway, it doesn't make a whole lot of difference when we're calculating. Okay, all right. And the units of current are, of course, the ampere. And 1 ampere is 1 coulomb. My computer's doing its thing again. Let me just check the charge. 70%, I think we'll make it. Okay, 1 coulomb per second, right? Okay. All right. So let's look at a line of charge. So think of a line of charge now. Now we've seen a line of charge before, right? It's just like, imagine just a charge kind of smeared out on a line. But imagine now that that whole line is moving like this, right? Okay, at some velocity v, then we would have a line current. Okay. And that's really what the current down a wire is, right? Okay, line current, it's a charge, a line of charge lambda, right? Traveling down a wire at speed v. Okay, so this would make current is equal to I, oh, sorry, not I equals lambda v, okay? All right, because a segment v delta t carrying a charge lambda v delta t passes a point P every delta t, right? Okay. Now we usually say the current is a vector, right? The vector nature comes from the direction of v. Yeah. So we would say this is the case. Now, as you'll see, we kind of, when it's convenient, we decide where to put the vector nature of I. Okay, you'll see that in a second. So we're only gonna now think about it a little bit. Now I know that lambda is usually our charge density, linear charge density, but here we're really using it only to represent moving charges, not just a static charge, right? So it's kind of tied to V, right? Okay. All right, so how do we write the magnetic force on a segment of current carrying wire? All right, so if we want the magnetic force on a segment of current carrying, carrying wire. All right, we know that it's F mag is Q V cross B, right? Well, we now have to add up all the charge because it's not just a point charge somewhere, right? Okay, so we can say F mag is equal to the integral of V cross B, and then DQ, right? But I know that that DQ is going to be just lambda DL or DR if you like. I tend to use DL a lot in this section, but remember that's the same thing as notationally as DR. Lambda DL, okay. But we know that lambda V is the current. So we can say that this is I cross B DL, right? And we can also say, hey, let's just write DL as the vector. Okay, this is where we get a little confused, right? So just don't get confused by this notation if you can help it. You'll see this all the time, but it's a little weird because all of a sudden we have a differential in the cross product. So what I mean is, remember that DL is along the wire, right? So I can just take I, the current, and you're going to see later that we're not going to consider any kind of current that's not constant along the wire. We haven't really made that formal yet. But I can just say, hey, look, I'm going to take the vector of nature and stick it onto the DL, not on the on I. Okay. This is why I said we're going to be playing fast and loose with the vector nature of I. And so this becomes DL cross B. Okay, it's a little weird to have your differential in there, but remember you would be doing this cross product first, right? Before you do any integral. And then if we have a constant current here, right? Which we're always going to have actually. DL cross B. Okay. All right. So when this was for a line of charge, let's think of charge flowing across a surface. Okay, so imagine you had a piece of paper like this, and charge might be flowing down this surface, like a ribbon charge or something. Yeah. Okay. So let's look at that. You can see we're just kind of doing setup today, basically. All right. So we're gonna look at charge flowing along a surface. Okay. So, and we're going to describe this in terms of a surface current density. Now here's where another unfortunate notation pops up, because this is K and it's not capital K usually, it's little k. And we use K for that 1/4 pi epsilon naught. We sometimes use K for constants. But this is kind of universally a surface charge density K with a vector. Okay, so let's delve into that. Okay, so let's consider, so let's say we have like, you know, a little sheet, like a sheet of paper. Maybe that's kind of a wrinkly sheet of paper. And then we have a ribbon of infinitesimal width here. Is that a little ribbon? And this is, oh boy, I can't read that. Hello. DL perp, yeah. This is going to be DL perp between these two arrows, right? DL perp. Can you read that? It's really somewhat long. Okay. Okay. If the current in this ribbon is DI, so if, let's do a different color, sorry. Is DI, put a little vector sign over that, then we define K, the current density, as DI DL perp. Okay, now these are this, oops, sorry, shouldn't be a vector on that actually. DL perp, okay. And so this is the current per unit width, right? Because the DL is like this little width. Yeah, does that make sense? Yeah. It's hard to get your head around a little bit. If if we have a mobile surface charge density, right? So imagine now we have a surface charge, but that in density, surface charge density, and that's moving with some velocity v. We could also write k as the charge density times v. Okay. And again, if that charge density is really only meant to be for moving charges, right? It's very clear. All right. So, and then we can write down the magnetic field, force. Okay, due to some external field on that ribbon of charge. Well, same old, we've got to take B cross B and then DQ. And in this case, that's integral V cross B and then sigma dA. And then we can now kind of pull everything in and write this as the integral of K cross B dA. Yeah. All right. This generalizes to volume current. Okay. Let's go to volume current. Can I go to the next layer now? Yes. Oh, go ahead. Okay. So now let's look at a volume current. All right. So if we have like some little weird shaped tubey thing, right? There'll be a little dA here that's perpendicular. And we have, you know, now this is a little chunk, right? It's like a little square cubic chunk thing that goes back, right? Or you can think of it as just being a little square area that extends down, right? You see what I mean? Okay, so there's this dA perp, and we say that J, so we have that volume current density. J is going to be DI, and this is a vector J, DI, dA perp. Okay. How is the current changing as you move that dA, right, around in the volume? Okay. And we could also write in terms of the volume charge density, right? J equal rho V, right? So you might have a volume charge density, the whole charge density is kind of moving down, right? Okay. And of course we can write this as the force due to an exterior magnetic field on this guy would just be the integral of J cross B, again, with the same thing that we just did, d tau, where I add up dq, et cetera. I skipped a couple steps. Okay. So this is equivalent to getting where we did with the electric field, kind of writing down things for line charges, surface charges, and volume charges. Here, we're just getting the forces. We haven't actually told you at all how to get the magnetic field given just the current densities, right? That's the next section. So this is just like, how do you calculate the force due to an exterior magnetic field on some current flowing over here, whether it's line current, surface current, volume current. Yeah, that's all we're doing here. All right. Let me see for a second. No, what we got? Let's do a couple examples. I need to layer up here. I want to move up here. Okay, never mind. All right. So let's do an example of if we have a current I that's uniformly distributed over a wire of circular cross section. Okay. All right. So example A is we have a current that's uniformly distributed over a wire of cross section, circular cross section with radius A. We want to find volume charge density. Okay, J. Okay, I know that J is DI, DA perp. Well, think about this wire, right? This wire looks circular cross section, looks like this, right? And it has a radius A. Yeah. Okay. So it's a constant. It's uniformly distributed, right? That means it's constant everywhere. I. Okay. And all we need to figure out is what is A perp, right? Because this says DI over DA, but I can just write this as I over A perp, right? But A perp is just the area of a circle of radius A, isn't it? That's the perpendicular area, isn't it? Yes. So this is going to be I over pi A squared. That is J. It's pretty simple when you think about it, right? You're looking for the area as this thing is kind of moving down like this, right? Think about the area moving down. Okay, cool. So let's do another example. Do I have room on here? Yeah, sure. So another example, B. Suppose current density in the wire is proportional to the distance from the axis. So we could write this as J is equal to some constant times S, if S is the distance away from the axis, right? Like we usually do in cylindrical coordinates, yeah? Yes? So we have the same kind of circular cross-section wire, but now that current density is not constant, okay? Like in the other case. All right, we want to know what is the total current going down the wire, okay? What is total current okay, what is total current going down the wire? Okay, well, I want to add up all the current, right? Okay, so to do that, I would do an integral, right? So I'd have I, oh, hello, I wanted it to be a different color. What's wrong with me? Oh, right, I is equal to the integral DI. But I know what the integral DI is, right? By the definition of J. That is the integral of J dA perp, right? Just from the formula in pink up here. Just from this. Yeah? Okay, now I got to figure out how to integrate that. Okay, what is dA perp? So what is dA perp? Okay, well, let's think for a second. We'll use cylindrical polar coordinates because we might as well. And so we know what's changing is S and phi, right? So think about, this is dA perp here, right? This is A perp, we know, right? So we think about what's changing. L, if you're, this is Z, let's say, right? Z isn't changing. right? But S's as we integrate, and we're going around the circle. So phi is as well, right? You see how we oriented the wire? Yes? Okay, so we know that dA is going to be this combination, and I always like to use this kind of thinking, dLs times dL phi, and in polar coordinates, that's S ds. Oh, sorry, my bad. It's ds and then S d phi, which is just S ds d phi, right? Okay. All right. So this means this is J, and I don't really need the vector nature of it, so I'll just leave it. And then S d phi, which is the integral of CS, that's our, I'll put that in yellow. That's our J. CS, and then we have another S, and then we have ds from 0 to a, and then we have the integral 0 to 2 pi of d phi. Okay, this becomes the integral of, I'll put the c out here, the integral of s squared ds 0 to a, and the integral, and this integral becomes just 2 pi, right? And so I get 2 pi c, and then s cubed over 3 from 0 to a, and that just becomes 2 pi c a cubed over 3. That is the total current. Yeah? Yeah, pretty simple, really. Yeah. All right, but very familiar, I hope, because we do things like this. Yeah. All right, let's look at one more thing. We have a couple short lectures. Okay, that's to make up for all the hard lectures. Okay. All right, we just saw that the total current, right? We just saw that the total current, I, you can integrate up J dA, perp, right? Okay. And I can write this as vector if I want. But really, oh, let me back that up. I don't need to write vector nature here. I'm going to point something out. But really, the perpendicular, the area that's perpendicular to the current density, I could write another way, right? I can write it as J dot dA, because that's going to pick out the perpendicular component of A anyway, right? Well, I hope that looks familiar, because I can immediately use the divergence theorem and change this to an integral over volume of the divergence of J d tau. Yeah. Okay, fine. Now, whatever flows out of the surface, right? So let's say you have some surface that's finite, and the charge is kind of is flowing out. That comes to the expense of charges that's in the volume, right? So imagine a case where you put some charge on something, and now you let it go to ground, right? All that's going to flow in time into ground, and you will not have any more charge. So there's some idea that whatever's coming out, right, has to equal that current, basically. So let's think about the charge. So let's think about the change in the charge, right? So I'm putting a negative on there because of the sign. We're losing charge. Oh, why did I do that? I didn't mean to do that. Sorry. Minus d dt, but I can write that total charge as the integral of the charge density over the volume, d tau, right? And I can pull that derivative in, minus the integral over the volume of d, and I can use a partial rho, partial t if I like, because rho could depend on other things, right? You okay with that? Yes, okay. So if we have current flowing out, right, there's some conservation of that current, of the charge, right? So once current is flowing, you can't just all of a sudden not have charge, right? So think of the idea of the charge going to ground. You're losing charge in your surface. So you need to have some kind of idea of what's leaving. So you can see here that we have the integral over volume of our del dot J d tau must be equal to then this negative of the change in the charge density in that tau, right, in that volume. Yeah, because that's the current flowing out. Okay, and so now that you have two integrals with the same, they're integrating over the same thing, volume, I can write down del dot J is equal to negative partial of the charge density with time. Okay, so this is called local charge conservation. But a lot of people just call it the continuity equation. Okay, that's going to become important later. More later. Okay. This is all I have for you today. This is just 5.1. And we're going to get into some nitty gritty of calculating magnetic fields tomorrow. I mean Thursday. My bad.